up in bicarb. If it's chloride, there's no change in serum anion gap. If it's due to other weak acidic compound like lactate in lactic acidosis, since we don't measure it, it inflates the serum anion gap. Sam, I see you raise your hand. Go ahead, ask a question. Or maybe you were just playing with the with the thing. I'm not sure. No? No question? Sam too? Ah, okay. So now let's make a proximal tubule. So this is a proximal convoluted tubule, and this is the PCT cell. And of course, on the basolateral side, fueling all the transport is sodium, potassium, ATPase. And it's thanks to this that any filtered sodium is going to be able to be transported. Now, of course, a major way that sodium is going to be transported is in exchange for proton, what we call the sodium proton antiport. And this is critical because as bicarb is also freely filtered, well, bicarb and the proton, they can be combined together thanks to a luminocarbonic anhydrase into, of course, H2O and CO2, which are freely permeable. And now intracellular carbonic anhydrase, since they're ubiquitous, gives you the proton and gives you the bicarb back. Well, for bicarb to now be retained, bicarb is exchanged with chloride for electroneutrality. So right now, if I'm inhibiting carbonic anhydrase with acetazolamide, or if I have RTA2, which is proximal convoluted tubule damage, secondary to heavy metals, toxins, Wilson disease, amyloidosis, what we call Fanconi syndrome, where we don't know the etiology, then what's going to happen is, number one, I can't reabsorb bicarb. So if I can't reabsorb bicarb, I'm going to get metabolic acidosis. But you see well on the diagram, if bicarb is not retained, chloride is not excreted. So of course, what happens to chloride if bicarb is not retained? Less bicarb retained, less chloride secreted. So I'm gonna see hyperchloremia. And as I see hyperchloremia, it now means the serum anion gap stays normal. So I have what I call a hyperchloremic metabolic acidosis. Is that okay? Yeah? So now, in reality, in a proximal convoluted tubule, there's also sodium coming in with glucose, coming in with amino acids, coming in with phosphates. So there's many other functions, and this that would be affected in RTA2. Now, not with acetazolamide. Acetazolamide only blocks carbonic anhydrase, but in RTA2 you would have also a deficit in reabsorption of glucose, amino acids, phosphate, hence potentially, for example, the hypophosphatemia that you would see in RTA type 2. So that's why I was telling you, well, at the very least, you don't expect hyper, but hypophosphatemia in that setting. Well, we now know also that don't forget the diuretic effect. So I'm going to say number 3, diuresis increases. So aldosterone increases, hence there is hypo, not hyperkalemia. And then comes the last portion for my question here, which is what's happening to the urine pH? Well, initially, urine pH is increased by the bicarbonaturia. But within days, any acidotic state causes distal intercalated cells to secrete protons in the tubule to fight the acidosis. Of course, the increased proton in the urine now acidifies it. So obviously, the increased pH of the urine is only transient. So there is only transient alkaline urine. So let me show you how this one works, so that like this, you'll be ready for that. So in the diagram, let's say it's the early collecting duct. And here, right here, are principal cells. Of course, principal cells, that's where aldosterone is going to work. And aldosterone stimulates its receptor and then changes gene expression. And what it changes gene expression of is, first and foremost, it'll increase sodium, potassium, ATPase pump. And second, what it'll do also is increase on the luminal side. I'll put them a little higher actually. Oops. Increase on the luminal side epithelial sodium channels. Of course, that means now you're going to be able to retain sodium, and to maintain electron neutrality, you'll be able to excrete potassium. You okay with the effect of aldosterone right now? So I left a gap, and if I left a gap, it's because in between here, intercalated cells. And look what intercalated cells do. To go back to the beginning of our evening, they take CO2 from Krebs cycle. They take water from electron transport chain. And with their carbonic anhydrase, they have a net production of protons and bicarb. If they're called alpha intercalated cells, they want proton and bicarb. Of course, bicarb is going to come in exchange with chloride, and that is bicarb and fight acidosis. That's the 4 to 5 days to full compensation, for example, that we were